On June 21st, 2025, the world's newest and most powerful survey telescope pointed its enormous camera at an unremarkable patch of sky in the southern hemisphere and quietly photographed something that, at the time, absolutely nobody on Earth knew existed. It wasn't looking for anything special that night. The Vera C Rubin Observatory, perched atop an 8,800-foot mountain in the Chilean Andes, was still deep in its commissioning phase, running routine, engineering tests to calibrate its instruments before its official science mission had even begun. 10 full days later, on July 1st, 2025, a completely separate telescope network called ATLAS, designed specifically to hunt for objects that might threaten Earth, spotted a fast-moving object streaking through the solar system and immediately flagged it as something extraordinary, only the third confirmed visitor from beyond our solar system that humanity had ever detected, an interstellar comet now known as 3I Atlas. It was only months later when a team of astronomers went back and combed carefully through Rubin's own early commissioning data that they realized the observatory had already captured the object in high-resolution images, completely by accident, a full 10 days before anyone on the planet knew it was even out there. Rubin hadn't just seen it. It had been quietly watching an enormous ancient visitor from another star system cross through our own cosmic backyard before a single human being had any idea it was coming. That single discovery, a telescope accidentally photographing something nobody knew to look for, turned out to be just the opening act for what's become one of the most productive and, in some ways, genuinely unsettling first years any astronomical observatory has ever had. To understand exactly why the Vera Rubin Observatory has been generating headline after headline since its cameras first switched on, you need to understand both what makes this specific telescope so different from everything that came before it, and exactly what it's actually been finding out there in the dark. The Vera C Rubin Observatory is a genuinely unusual instrument, built with a singular, obsessive focus that sets it apart from almost every other major telescope currently operating anywhere on Earth. Jointly funded by the U.S. National Science Foundation and the Department of Energy at a cost of roughly $800 million, the observatory's defining feature is the Legacy Survey of Space and Time, or LSST, a planned 10-year mission to photograph the entire visible southern sky over and over again, every few nights, using the largest digital camera ever built for astronomy, a genuinely staggering 3,200 megapixel sensor mounted on an 8.4-meter telescope. Most telescopes are designed to stare deeply and patiently at one small patch of sky for a long time, gathering as much light as possible from a single distant target. Rubin was built to do almost the opposite, scanning enormous swaths of sky, rapidly and repeatedly comparing each new image against everything it's already photographed, and flagging absolutely anything that's changed, moved, brightened, dimmed, or appeared out of nowhere since the last pass. That specific design philosophy is exactly why it managed to catch 3I Atlas completely by accident months before any human analyst went looking for it. The telescope wasn't hunting for interstellar visitors that night. It was simply photographing everything in its path, the way it's designed to do every single clear night for the next decade. And whatever happened to be sitting in that patch of sky got captured along with it. Once astronomers went back and properly analyzed what Rubin had actually recorded, the details of 3I Atlas itself turned out to be genuinely remarkable on their own, well beyond the strange coincidence of having been secretly photographed before its official discovery. Follow-up observations combining Rubin's own data with measurements from the Hubble Space Telescope determined that 3I Atlas measures roughly 7 miles, or about 11 kilometers across, making it the single largest interstellar object ever detected passing through our solar system, considerably bigger than either of the two interstellar visitors discovered before it, 1I Oumuamua in 2017 and 2I Borisov in 2019. The comet tore through the inner solar system at tremendous speed, and by the time astronomers had a clear picture of its trajectory, they confirmed something else. Genuinely dramatic, this object isn't in any kind of orbit around our sun at all. It arrived from interstellar space on a hyperbolic trajectory, meaning it's simply passing through, and having already made its closest approach to the sun back in October 2025, it's now speeding back out of our solar system entirely, moving at more than 60 kilometers per second, never to return. An object that visited our cosmic neighborhood exactly once, entirely by chance, after who knows how many millions or billions of years drifting silently through the empty space between stars. That last detail, how long this thing had actually been drifting before it happened to cross paths with our own solar system, is where the story shifts from merely remarkable to genuinely staggering. In June 2026, a team of scientists led by NASA astrochemist Martin Cordner published a study in the prestigious journal Nature that used isotopic analysis, gathered in part using the James Webb Space Telescope, to estimate 3I Atlas's actual age, and the number they arrived at is difficult to fully wrap your head around. The comet, according to that analysis, could be as old as 12 billion years, nearly 3 times the age of our entire solar system, which itself only formed around 4.5 billion years ago, and only slightly younger than the universe itself. The evidence behind that estimate comes from measuring the comet's deuterium content, a heavier form of hydrogen that only accumulates in significant quantities inside extremely cold environments. Cordner's team found 3I Atlas contained roughly 30 times more deuterium than comets that formed inside our own solar system typically carry, evidence pointing to an object that originally formed in an environment hovering somewhere around minus 243 degrees Celsius, one of the coldest formation environments ever measured for any object humanity has ever studied up close. Independent researchers working the problem from a completely different angle, examining the sheer velocity at which the comet was traveling when it was first detected, arrived at a broadly similar conclusion, reasoning that an object moving this fast must have picked up that speed through repeated gravitational encounters with other stars over an enormous span of time, encounters that would take billions of years to accumulate. Multiple independent lines of evidence, isotopic chemistry and orbital dynamics, both pointing toward the same genuinely mind-bending conclusion that this comet had likely already been drifting through the galaxy for something like twice the entire age of our own sun before it ever wandered close enough for anyone on Earth to notice it. An object that old and that strange inevitably attracted its share of genuinely wild speculation once it made headlines, and it's worth addressing that directly rather than pretending it didn't happen. A prominent astrophysicist at Harvard drew significant public attention by suggesting 3I Atlas might not be a natural comet at all, but potentially an artificial object, floating the possibility, however speculative, that something this unusual could represent evidence of alien technology passing through our solar system. NASA officials publicly rejected that specific claim, and the growing body of scientific evidence, the visible dust coma indicating genuine cometary activity, the isotopic signatures consistent with natural ice formation in a cold interstellar cloud, and the object's behavior matching what astronomers would expect from an ordinary, if extraordinarily ancient, ball of ice and rock, has continued pointing firmly toward a natural explanation rather than anything artificial. That doesn't make the object any less genuinely remarkable. An interstellar comet that's been drifting through the galaxy since long before the sun itself ignited, carrying inside it a chemical record of conditions from a part of the galaxy and a period of cosmic history that existed for billions of years before Earth was ever formed, doesn't need to be an alien spacecraft to qualify as one of the single most scientifically significant objects any telescope has ever managed to photograph. Quick pause here. Because if the kind of story where a routine engineering test accidentally captures evidence of a 12 billion-year-old visitor from across the galaxy is exactly the sort of thing that keeps you coming back to channels like this one, that's precisely the territory we keep digging into. If that's useful to you, go ahead and subscribe. It genuinely helps more of this research reach more people. The observatory itself carries a name with real weight behind it, honoring astronomer Vera Rubin, whose careful measurements of how fast stars orbit within distant galaxies back in the 1970s and 1980s provided some of the first compelling observational evidence that dark matter actually exists, work that reshaped modern cosmology, even though Rubin herself never received a Nobel Prize for it during her lifetime. Naming this specific instrument after her carries an obvious intention, since one of the observatory's core scientific missions over its full 10-year run is to map the distribution of dark matter and dark energy across enormous swaths of the observable universe by tracking subtle gravitational distortions in the light from billions of distant galaxies, essentially continuing at a vastly larger scale exactly the kind of painstaking observational work Rubin herself pioneered decades earlier. The sheer volume of data required to do that kind of HF mapping is itself almost difficult to comprehend. Each individual image captured by the observatory's 3,200 megapixel camera is large enough that displaying just one of them at full resolution would require roughly 1,500 standard high-definition television screens arranged together, and the telescope is designed to capture a completely new image roughly every 20 seconds, every single clear night, for 10 consecutive years, generating a total data archive expected to eventually reach into the tens of petabytes, an amount of information so large that processing it all requires purpose-built automated software pipelines running continuously just to keep pace with what the camera captures. Understanding where 3I Atlas fits into the broader, still very short history of interstellar object discovery helps put its significance into proper context as well. Before 3I Atlas, astronomers had only ever confirmed 2 other objects definitively originating from outside our solar system. The first, 1I Oumuamua, was spotted in 2017 by a telescope in Hawaii and immediately became the subject of intense scientific debate, specifically because of its unusual elongated shape and its strange, unexplained acceleration, as it moved away from the sun. Details that fueled some of the earliest serious speculation, including from the same Harvard researcher who would later make similar claims about 3I Atlas, that the object might not be a natural phenomenon at all. The second confirmed interstellar visitor, 2I Borisov, arrived in 2019 and behaved considerably more like a conventional comet, giving astronomers their first genuinely clear look at cometary material that had formed around a star other than our own sun. Each of these three interstellar objects, discovered roughly 2 years apart from one another, arrived essentially at random with no advance warning and no way for astronomers to predict when or where the next one might appear. That pattern is exactly why an instrument like Rubin, built specifically to continuously monitor the entire sky, rather than search only in narrow targeted patches, represents such a genuine leap forward for this specific kind of discovery. Scientists studying the population of interstellar objects passing through our solar system have estimated that Rubin's full 10-year survey could detect dozens of additional interstellar visitors over the course of its mission, transforming what has so far been an exceedingly rare, almost accidental category of discovery into something approaching a routine, expected part of the observatory's regular output. As remarkable as the 3I Atlas story is on its own, it actually represents only a small fraction of what the Vera Rubin Observatory has managed to accomplish since its cameras first switched on. And the sheer scale of everything else it's found in barely a year of operation is, in its own way, just as genuinely stunning. The observatory released its very first public images back in June 2025, revealing more than 10 million galaxies visible in a single field of view, along with swarms of asteroids scattered throughout it. Our own solar system, more than 1,500 of which were immediately confirmed as objects nobody had ever cataloged before. That was just the opening act. In April 2026, the Rubin team announced they had submitted more than 11,000 additional newly discovered asteroids to the International Astronomical Union's Minor Planet Center, the official global clearinghouse for confirmed asteroid and comet discoveries, based purely on data gathered during preliminary optimization surveys conducted before the telescope's real 10-year science mission had even formally begun. Mario Juric, the University of Washington astronomer who heads Rubin's solar system science team, described that haul in blunt terms, calling it just the tip of the iceberg and noting that discoveries which used to take astronomers years or even decades to accumulate, Rubin was now managing to deliver in a matter of months. Buried inside that same batch of 11,000 fresh asteroid discoveries were 33 previously unknown near-Earth objects, the specific category of asteroid that orbits close enough to our own planet's path to warrant genuine ongoing monitoring for any potential future impact risk. That detail connects directly to arguably the most consequential and most genuinely important part of Rubin's entire mission, its role in planetary defense. Once the observatory's full 10-year survey gets fully underway, scientists expect it to eventually discover as many as 11,000 new asteroids every single 2 to 3 night observing period, a discovery rate that would, over the full course of the mission, triple the total number of known asteroids in our entire solar system catalog. Researchers involved with the project have stated that Rubin is expected to double the number of known near-Earth objects specifically, including a meaningful share of asteroids larger than 460 feet across, the size threshold generally considered large enough to cause genuinely serious regional or even global damage in the event of an actual impact. For an observatory that's already managing to find tens of thousands of new objects before it's real. Mission has even formally started. The eventual scale of what Rubin is expected to map out across our own cosmic neighborhood over the coming decade represents something genuinely unprecedented in the entire history of astronomy. The telescope's discoveries haven't been limited to simply counting and cataloging new objects either. In a peer-reviewed study published in January 2026, astronomers using Rubin's early test data identified an asteroid, formally designated 2025 N/45. That turned out to be the fastest spinning object of its size ever recorded anywhere in the solar system. The asteroid measures roughly 710 meters across, nearly the length of 8 football fields laid end to end, and yet somehow manages to complete a full rotation, once every 1.88 minutes, an almost unbelievably fast spin rate for an object of that size. Researcher Sarah Greenstreet, who led the study, noted that Rubin's specific combination of imaging power and observation frequency had allowed astronomers to study an entire population of relatively small, extremely fast rotating asteroids that had simply never been reachable with previous telescope technology, objects whose existence hints at collision histories and internal structures. Scientists are only just beginning to understand. 2 additional record-breaking fast-spinning asteroids turned up in that same early data set, all discovered before the observatory's real, decade-long survey mission had even officially begun. The observatory reached another genuinely significant milestone on February 24th, 2026, when it formally activated its real-time public alert system, a network designed to notify astronomers around the entire world, instantly and automatically, whenever Rubin's cameras detect something that's changed in the sky since the last time that same patch of space was photographed. On that first night alone, the system generated roughly 800,000 separate alerts, flagging everything from newly detected asteroids moving through our own solar system to distant, exploding stars flaring to life in galaxies far beyond our own, and countless other subtle changes scattered across the observable sky. That single number, 800,000 notable changes detected and flagged in one single night of observing, gives a genuine sense of just how much activity is constantly happening across the universe that, until an instrument with Rubin's specific combination of speed, resolution, and repeated coverage came online, had simply been going completely unnoticed by anyone on Earth. After a commissioning and testing period that stretched longer than originally planned, the observatory's actual 10-year legacy survey of space and time formally began in July 2026. Following what CNN described as an unprecedented, deliberate 10-year mission specifically designed to build the most complete inventory of the solar system and the wider Milky Way galaxy that astronomy has ever attempted to assemble, while simultaneously chipping away at one of the biggest remaining mysteries in all of physics, the true nature of dark matter, the invisible substance believed to make up roughly a quarter of the entire universe's total mass and energy content. Everything the observatory has already accomplished, the secretly photographed interstellar comet, the 11,000 new asteroids, the record-breaking, fast-spinning space rocks, and the single night that generated 800,000 cosmic alerts all happened before that real, decade-long mission had even formally gotten underway. Rubin's full survey is now expected to run for 10 consecutive years, repeatedly rephotographing the entire visible southern sky, comparing each new image against everything that's come before it, and flagging absolutely everything that changes, moves, or appears for the very first time. Set against that entire trajectory, the story of 3I Atlas starts to look less like an isolated lucky coincidence and more like a genuine preview of exactly what this specific telescope was always built to do. An object that had been silently drifting through interstellar space for as long as 12 billion years, carrying a chemical fingerprint from an era of cosmic history that predates our entire solar system by billions of years, happened to cross paths with our own cosmic neighborhood. At almost exactly the same moment, humanity finally finished building an instrument specifically engineered to notice things like it, whether anyone was actively looking for them or not. Rubin didn't need to be searching for an interstellar visitor to catch one. It simply needed to be doing what it was designed to do, watching the entire sky, constantly, patiently, and missing nothing. And an ancient traveler from somewhere else in the galaxy happened to wander directly into its field of view 10 days before anyone on the planet even knew to look up. That's really the genuinely unsettling, genuinely thrilling promise sitting at the heart of everything the Vera Rubin Observatory has already accomplished in its first year, and everything it's now positioned to keep finding across the next decade of continuous, unblinking observation. Somewhere out there, right now, scattered across the roughly 11,000 new asteroids already cataloged, the tens of thousands more expected every few nights once the full survey ramps up, and whatever else happens to drift through the telescope's field of view purely by chance. The way 3I Atlas did, there are almost certainly more genuinely strange, genuinely ancient, genuinely unexpected objects still waiting to be noticed. The only real question left is what Rubin's cameras happen to be pointed at the next time one of them quietly drifts through. If you want to keep following exactly what the Vera Rubin Observatory finds next, now that its full 10-year survey is finally underway, that's precisely the kind of story this channel keeps tracking closely as it develops. So stick around for the next update. Let us know in the comments what you find most remarkable about all of this. The fact that a telescope accidentally photographed a 12 billion-year-old interstellar visitor days before anyone knew to look for it. The sheer scale of 11,000 new asteroids discovered before the real mission even started. Or the fact that we're now only in the very first year of a 10-year survey that's already reshaping what we thought we knew about our own cosmic neighborhood. See you in the next one.